So hello dear students. Now in this subunit I'm going to discuss the radioactivity which is either growing or decaying. That is radioactivity which is either increasing with time or decreasing with time. So both these possibilities are there. Generally in most of the cases radioactivity decreases in time, but sometimes in successive disintegration there is a chance that radioactivity is increasing as well. So I'm going to discuss the basic law of radioactivity and how it results in the decay of radioactivity and in some cases the growth of radioactivity. So some elements like thorium and uranium exhibit radioactive phenomena which does not change with time. Basically, why it is so? Because uranium and thorium, the decay is taking place very slowly. So during the period of observation, you will not see any decay or decrease in the activity of these materials. But some materials like radon exhibit radioactive phenomena which change rapidly with time during the period of observation. Why is it so? This is the topic that we are going to understand in this subunit. So generally radioactive materials, the activity reduces in a regular manner. So it was first observed by a British scientist named William Crookes, who observed in 1900 that there is some unknown substance present in the uranium salt which was chemically precipitated, carried away the entire radioactivity of the uranium salt. So basically what he did was he precipitated out some material from the uranium salt, and then the filtrate or the precipitate that he got was carrying whole of the radioactivity, and the uranium salt or the original salt lost almost all of its activity. So he named this curious and mysterious material which was in the precipitate form and which carried away the whole activity of uranium as uranium X or UX. And now it is known as thorium-234 or protactinium-234 depending upon the isotope of uranium that we are using. So the key aspects of this experiment, which was conducted in 1900, the first thing that he did, he precipitated this or separated this UX from the uranium salt. So what he did, he precipitated out uranium nitrate from the solution and found that the remaining filtrate was more radioactive than the uranium itself. The filtrate was named as uranium X. Then with the help of the device that he had created himself, which was known as spinthariscope, he measured the radioactivity of this UX, and he found out scintillations or flashes of light caused by the alpha particles which are hitting some zinc sulfide screen which was a part of this equipment, and he found out that this UX is highly radioactive. But then he found out that the activity of this mysterious element UX is decreasing with time, and in orders of days its activity almost vanished, whereas the uranium that was left in the salt, its activity was regained. The activity of the uranium salt which was filtered out, it it grew, or the radioactivity increased for that particular separated material. It was also one of the first instances of or the demonstration of radioactive transmutation, that is, one radioactive substance is transferring or changing into another radioactive substance. So Crookes' work helped reveal that radioactivity involves sequence of decaying substances, which are known as decay chains. And that was a major shift in the understanding of radioactivity. The UX was as I've told you earlier, was identified as thorium-234, which was a decay product of uranium-238. And later on, Ernst Rutherford and later other people started mapping the uranium decay series. They started finding out the total series starting from uranium and ending into the final material, which was non-radioactive. And they found out there are several intermediate nuclei of different elements, and uranium converts into the stable nuclei in a step-by-step manner involving a lot of intermediate nuclei, which are also radioactive, and they form a kind of a chain starting from uranium to the last element, which is totally stable. So here in this figure, a spinthariscope is shown, which is basically a vessel in which when the radiation enters this vessel, it ionizes, and either a phosphor or a scintillator is there to measure the radiation or the amount of radiation that is coming inside or entering this device. So here we show the activity of UX. So you can see the activity of UX is decreasing with time in the number of days, whereas the activity of uranium is increasing, and you find out that they are having a symmetric or a mirror image like formation. That is, if you can see that the amount by which the UX decreases, by the same amount the activity of uranium increases. So the activity of UX is actually decreasing by the same amount as the activity of uranium is increasing. So the net activity is always constant at all values of time. So Crookes showed that the activity of UX and U, that is uranium and the mysterious separated material, which was later found out to be thorium, is shown by these two expressions. The activity of X was A naught exponential minus lambda T, and AU, which is the activity of uranium, was A naught 1 minus exponential of minus lambda T, where A naught and lambda were two constants which were common to both the equations, and T is the time after the separation of UX from U. So basically what is happening is UX is also radioactive, and when it is precipitated out, it is actually the UX which is carrying the radioactivity. U itself has a lower activity which is not actually measured by the device that was invented by Crookes. So the activity of U was not measured by the Crookes device, whereas that of the UX was measured by that device. Actually, U was emitting an alpha particle which was not penetrating that much, so it was easily absorbed, whereas UX was emitting beta rays which were highly penetrating and were not absorbed. So they showed out in the measurement of the device. So after separation, the whole activity was carried away by UX, but then as UX transmutated into a more stable nuclei, the activity of UX was lost, whereas uranium decayed into UX, and so as the concentration of UX increased after the separation inside the uranium salt, the radioactivity of that particular separated uranium was shown to be or found to be increasing. So later on, Rutherford and Soddy devised a law based on the experiment conducted by Crookes, and they found out that the radioactivity actually follows an exponential law, and that law can be summarized by this form: dN by dt is equal to minus lambda n, where dN by dt is the activity of the material and it is the rate of change of the number of nuclei which are decaying or which are present inside the radioactive material. And this is basically equal to minus lambda n. So lambda is a decay constant and n is the number of nuclei, the radioactive nuclei, which are present at that particular time. So the rate of change of those nuclei is proportional to the number of nuclei that are present at that particular time. So the solution of this equation is simply, it's a first order differential equation, and this equation has a solution which is exponential. N of t is equal to n naught exponential minus lambda t, where n naught is the initial number of nuclei at t is equal to 0. The half-life of from the law, you can see what is the basically the time in which the number of nuclei become half. So you can see here n naught by 2 would be given by n naught exponential minus lambda into t half. Dividing both sides by n naught, we get half is equal to minus exponential minus lambda t half. Taking the natural logarithm, we can say logarithm of half is equal to minus lambda t half. So t half becomes logarithm of 2 divided by lambda. So the relationship between lambda, which is the decay constant, and half-life is given by this formula. T half is equal to logarithm of 2 minus divided by lambda, as you can see here. So if you know lambda, you can find out the half-life or the time in which the material reduces to half of its original value. So here we show a graph. In this case, 100% of nuclei are present for 3 different types of nuclei, having 3 different types of, or 3 different values of lambdas: lambda 1, lambda 2, and lambda 3. Now lambda 1 is greater than lambda 2 and lambda 2 is greater than lambda 3. So lambda 3 is the smallest, whereas lambda 1 is the largest. And in that case, what is seen is that the decay is slower for lambda 3. For the smallest value of lambda, which is lambda 3, the decay is smallest, and the decay is fastest for lambda 1, which has got the highest value amongst the 3. Also, you can see here that if you plot log of the activity in microcuries versus the time, you can see since the activity follows an exponential law, the log of the activity would be linearly related to time. So basically, when you plot log A with respect to time, you just take the log of the activity, and since activity is exponentially related to time, the log of the activity simply is going to be related linearly with time. So you'll get a straight line when you plot log A versus time, and it will have a negative slope, and the negative slope would be equal to minus lambda, which is the decay constant. The negative of lambda would be the negative slope of this particular graph. So from this graph, if you plot log of A with respect to time and you measure the slope of this graph, you can, from the slope of this graph, you can find out what is the value of the decay constant. And then from the decay constant, you can find out the half-life, as from the earlier formula, as I've shown you in the previous slide.